Hello, Kirtana, I'm audible.
Yes, sir.
Okay, Kirtana. So today we'll be starting with Kirchhoff's current law. Okay. So Kirtana, first one is Kirchhoff's current law. In the last session, I gave you example of your analysis of electrical circuits, right? What kind of circuits we can have? A circuit where we can give given a direct series and parallel combination, where you can just figure out get the voltage across the circuits, right? Then we can have a circuit where you can't actually figure out a proper parallel and series combination in the circuit. So if this is the case, you can't solve the circuit because you are not able to calculate the R equivalent, right? Whatever the V, if I ask you, you won't be able to do this, right? So for this, we have two laws to talk about. One is Kirchhoff's current law, and what is the another law, Kirtana?
Kirchhoff voltage law.
Exactly, Kirchhoff's voltage law. Okay, so the first discussion is about the Kirchhoff's current law. Yeah, we can rewrite the same thing as KCL. Okay, in most of the cases, we won't be writing the complete thing. So what is this? This law is all about distribution of current at a junction. Okay, in given circuit. So assume I'm giving you like this. So Kirtan, if this is the circuit, I can simply say this is a point, this is junction point. Can I say this? Yeah, because multiple wires are meeting at certain point, right? So if I say Kirtana, some current I is going. Okay. So you know that the some because look, there's a no current going to be adjusted at this point, right? I can say some current is going in this way, some current will be going in this way, some current is going with this way. Okay, so the relation which will be that I1 is equals to I2 plus I3 plus I4. Okay, if I say Kirtana, this is incoming current, these are the outgoing current. If I ask you Kirtana, what is the incoming minus outgoing? So you will say this will result me the total current absorbed or the something you can say collected by this junction potential. If you see with this equation, that is supposed to be zero. So what I wanted to say is the net charges accumulated at the junction potential is going to be zero. Is that clear? So what it means that whatever the current is coming out, that is going to be like that whatever the coming whatever the current is in, the same amount of current will get outside. But if there's multiple wire, it will get distributed. Okay, the distribution will depend upon what kind of resistance are there in the further in the wire. Okay, on the basis of that it is going to go. But yeah, you can say total current is going to get distributed into four, not four, like multiple wire, whatever the number of wires are there, it will get distributed over there. Is that clear, Kirtana?
Yes, sir.
Why this happens? Because look, the total charge of the system is conserved, right? You know, when I'm saying current is flowing, what is the current? Current is basically because of some electrons are flowing, right? Assume that I'm showing you four in a 1 second. It is all things happening. Okay, four electrons are flowing. So I can simply say if 4 ampere of current is going, so I will say four electrons are going in this way. But from where these four electrons are coming? These four electrons must be coming from these wires, right? Assume one electron is coming with this way, one electron is coming with this way, one electron is coming with this way. So you will say 1 ampere has been shifted here, one is going here, one is going here. Okay. You can't say, look, if you say four is there, one is there, two is there, like one is there, and zero is there. Or you can say two is there. Okay. Yeah, one should be two actually. Assume it to be two. Zero is there. So the sum of these will come out to be only three electron, right? But here you need four electrons. So basically, because charge is conserved, whatever the charge going this way will pass to this way also. Okay. So due to the conservation of charges, you can say the current is going to be distributed into multiple direction. Although, even though it depends upon the direction, you can say its summation is done a scalar summation, right? Scalar addition. Current goes with a scalar addition. Okay, that's why this is a tensor quantity. Is that clear?
Yes, sir.
Okay. So whatever we have written over here is that is due to the conservation of charges. You can say that I1 minus I2 plus I3 plus I4. Keep the directions together. Zero. So you can say that what this is. This meant the total current at the junction. At the junction, the total sum of all outgoing current will come out to be zero, right? You can say that at this point, if I ask you what is the current going, you can say at this junction, I1 current is going inside and the same amount of current is going outside. Okay. So what is the total incoming current to the junction? That comes out to be zero. Is that clear, Kirtana?
Yes, sir.
If I ask you how you can rewrite the same thing, look, go with the definition. KCL says that at junction of a circuit, total sum total sum of all outgoing currents in all branches at junction is zero. Okay, it means Kirtana, if you see any junction, okay, total current coming towards that junction is supposed to be zero. How in above case, if I just take the example of above case, this was the junction, 3 points were there ongoing. So I2 was going there, I3 was going there, and I4 was going there. I1 is going there. I said Kirtana, total current coming towards this junction should be zero. So I can say this I1 is going towards the junction, so I will write it as I1. Okay. So Kirtana, how I should write I2 such that it will go in this? I know that I2 is going this way, but I want the current which is going this way. So can I say that Kirtana minus I2 is going towards this way?
Yes, sir.
So same I will doing for other twos. Okay. And the summation of all these is supposed to be zero. And you can say we have got the same equation of the vector, the current addition in this KCL law also. Is that clear?
Yes, sir.
All right. So what you can say is, in another word, okay, you can do this in two ways. You can say all incoming current or outgoing current. In this particular case, whatever example we have taken here, in this taken, we didn't took the example of outgoing current, right? You can see we were taking the current which are going towards the I. Okay, if you do in another ways, outgoing mean to say the current which is going away from the junction. So which are the current going away? You can say I2 is going away, I3 is going away, plus I4 is going away. How you will write this in the terms of away? It is going this way. So what is the current of this I1 which is going away? You can say this part, right? So you just have to change the direction. So it will become minus I1. This is the away going conditions. You can say that at the end of the day, when you take all these to other side, you are going to get the same equation. Can you see this, Kirtana? It's up to you. Current, all the currents going towards the junction or all the current going away from the junction. Just take one thing, either away, either towards. That is supposed to be zero. Is that clear?
Yes, sir.
Okay, just two ways are there to understand the same thing. Okay. I is equals to 1 to total. I out is equals to 0. Basically, total current going outside towards the junction. Yeah, sir. 1 to n. I in. Okay, two ways. So let's talk about some application. I'll just I'll give a circuit over here. Okay, so Kirtana, look, if I ask you what is the current in the different, okay, Kirtana, do one thing, calculate the current flowing across 4 ampere, 4 ohm and 3 ohm and 6 ohm. Look, right now, actually, we don't really need the use of this KCL or KVL part, but we will see when we will be using, right? Because we have solved this equation earlier also. So just try to solve this once again. What is the current flowing for 3 ohm, 6 ohm, and 4 ohm? This is what we have to solve for now. Okay. Kirtan, have you solved this one?
Solving, sir.
Okay.
So the current through 4 ohms is 3.3 amperes. For 3,
How much, Kirtan? Hello, Kirtan.
yes,
Okay,
sir.
how much
For
current? Yeah. How much current for this one?
3.3.
3.3, okay. Yeah, this is 3.3, and then after the rest of two.
1.8 and 1.5.
Oh, so let's see will it be correct or not. Okay. So, okay, so if I just ask you what is the uh, R equivalent of this circuit, so this is coming out to be like for this one it is in the parallel, so you will say 3 into 6 by 9. This comes out as 2. Okay, 2 plus 4. This comes out as how much? Total current is total resistance is 6. Okay, in this, so you can say I comes out as 20 by 3. No, this is 6 actually. So it returns you 3.33. Okay, and so on. So that's correct. That is fine. And we look now from here because you know the total current getting inside is I1. Total is I, right? Um, we have already studied a way how to calculate resistance like current flowing through this one. Okay, when you know the total current is getting inside is I and you know the resistance, right? What is that way? You can say I1. Assume I'm saying this is I1, right? And this is I2. So I1 is nothing but total current multiplied by other resistance 6 and divided by sum of both. No, this is 2 by 3 actually. 3 to 2 this. So 2 by 3 is equals to what is that? 3.3. So you can say 1.1. What is it? 2.2. Okay, other one is 1.1. This is what you are supposed to get the answer. Okay. Uh, yeah. Like for this one, if you wanted to calculate, it will coming out to be I into 3 by 9, and this is 3.3. So yeah, you can see 3 1.1. Is that clear? So Kirtana, from here it will be 3.3. From here it will be I think 2.2, and here it should be 1.1. Okay. You can see this is also balancing, right? 3 into 2.2, 6.6 is the resistance across this terminal. Okay. 6 into this, it is also 6.6 voltage across the terminal. Is that clear, Kirtana?
Yes, sir.
Any doubt? No doubt, right?
No, sir.
Okay. Okay, Kirtana. So how we can do this problem using KCL? Okay. My task is to do the same problem using KCL. Although this problem we don't actually need the KCL because it's kind of complicated in these small problems. Okay, we have to look where you should use this or not. Okay, so Kirtan, assume that I am saying total current in the circuit is I1, right? Okay, so this is the current it is going from I1. Can I say that whatever the current going inside that like this way, it is also coming this way also? So I can say here also the current is I1. Is that clear, Kirtan, till here?
Yes, sir.
Okay. Okay, assume this is I1. So you can say here the current is going is I2 in this branch, and this branch it is I3. So can I say that, Ketan? Let's try to apply KCL at this point. This is A junction. Okay? KCL at A. So if you do this, what you are going to go as, you will say, let's look all the currents going towards this junction. So I1 is going right. What about the I2? It is away. So make it this I3. Again, this is like, so can I say this? I1 is equals to I2 plus I1. Although we know this equation by using a simple, what I can say, the vector addition and all, right? But we don't have to do this, okay? We don't have to solve this by using this. Just remember this equation, okay? We will see how to apply this equation, okay? So I'll try to remove all this. Kirtana, let's write all the possible voltage. So Kirtana, what is the voltage at this particular terminal? Can I say this is to be 0?
Yes, sir.
Okay, so at this point you can say that the voltage is 0. That's fine. um, you know at this terminal their voltage is 20, so I will say till here the voltage is 20, right? Till
Yes,
here
sir.
the voltage is 20, but what about this terminal? We don't know, right? Assume it to be the x. You can assume it to be the x. So Kirtana, if you see in this branch, from where to where current is going, can I say that current is going from this way to this way? So what it will be, can I write this I1 is equals to potential difference across this terminal? What is the potential difference? 20 minus x. Why I'm not writing x minus 20? Because I have assumed direction of current to be this much, right? And current always goes from higher potential to the lower potential. Is that clear, Kirtana?
Yes, sir.
So I made I1 is equals to this by this. Is that clear?
Yes, sir.
Okay. If you look at this, current is like potential here is x, here it is 0, current flowing is I1. So can I say that I2 is equals to x minus 0 divided by 3, and similarly I3 is equals to what is it, x minus 0 divided by 6.
Yes, sir.
Okay, why we did this? If we just put all these value over here, okay, 20 minus x, instead of I1 we have to put minus, instead of like negative sign is there, instead of I2 put this equation minus, instead of I3 you have to put x minus 6. So what if you solve this case, now what you are supposed to get is you will be getting the value of x. What is the x? X is the basically what is the potential at this particular point. Okay, this is the reason. Okay, this is a good way to solve it. And if you know the potential at this particular point, you can solve the current also, right? Just dividing it by the resistance. And also, can you try to get me the answer from this one?
Yes, sir.
Okay, so get me the answer for this one. All right, I'll just give you directly. The x should be 6.6. Okay, voltage. Understood, Kirtana? I have solved it, so I know the value. Another way is how I directly got this, because I know this is supposed to give me the potential at this point. And in the previous, when I solved it, I told you to solve it in a normal method. You got the potential across this is 6.6, right? So you can say the potential difference is equals to x minus 0 is equals to 6.6. So I directly know this method. I solved it in the previous, like whatever the method we used in the previous, we already got there. Okay, so this is what I did. Any doubt, Kitna, here?
No, sir.
Look, if you have any doubt, just let me know. Okay, this is a method, an application of KCL, you can say, where we have got the same. Look, we have got the same thing using this method, right? Okay. So now, if I ask you what is I1 and I2, you can simply say that I2 is equals to x 6.6 divided by 3, 2.2. I1 is equals to x by 6 is equals to 6.6 multiplied by 1. Okay, same thing. Look, you have got the same, just methods are different. This can be kind of complicated, or because it's not a short form. Okay, the earlier method which we have already used, that is a very short form. Okay, so you just have to look at the problem, like what kind of problem is there, what kind of equations I should use. It should be your convenient. Okay, and the problem should be solved in a minimal time possible. And if I, okay, this should be I2 maybe. Yeah, this is I3 actually. And if I ask about I1, so that is how much is that? Yeah, I1, if you see, I1 is 20 minus x. So you can say 20 minus x divided by 4. So x is 6.6. So this comes out as 13.4 divided by 4. So yeah, the answer should be something around 3.33 again and again. So that's what the answer comes out. Okay, that's it. Any doubt, Kirtana?
No, sir.
Okay, so yeah, we did KVL, KCL by this. Okay, I'll move to the new page and we'll come up with a KVL. Hashtag Kirchhoff's voltage law. Okay, okay. So Kirtana, this law is basically is also terminal as loop rule. It's not terminal, it should be termed as This loop, like this law is also termed as loop rule, okay? Because this is more about the loop for electrical circuit. It states that in any closed loop of a circuit, the sum of all EMF of loop and potential drop. Look, when we say potential drop, Kirtana, potential drop happens across some device that can be resistor, that can be some bulb, any electricity consuming device. Okay, potential drop across all resistances of loop is equated to be zero as zero. Okay, Kirtana, just tell me, what do you understand when I say potential drop across resistor? Kirtana, what you understand when I say there is a potential drop across resistors?
The potential decreases.
No, that's not actually. Basically, Kirtana, potential drop when I say is, look, whenever you are having a resistor, it is connected with some battery. Okay? What happens is when we pass some current, potential drop means how much is the total portion of the current, like how much the total portion of voltage has been dropped across these two terminals. Okay? This is what we see about the potential drop, and you can simply say how this is dropping. Dropping means to say used of some energy, right? So when some current passes across a resistor, what is the potential across that? That is IR. So this is what the potential is dropping, okay? And it always drops from higher to lower. It means if current is going with this way, it means there must be higher potential at this side, lower potential at this side. Is that clear, Ketanu? Okay, current
Yes.
always goes from higher potential to lower potential. This is what you should care. So assume Ketana, I'll be making one circuit. This is R1. This is E1. Okay, EMF. I said all the EMF and all the potential drop across a resistance. If you go in a loop, that results out to be zero. This is A2. Okay, so I'll just mark some points. This is A point. This is B. This is supposed to be C, and this is supposed to be D. Right. So with this loop, what it says that in closed loop, A, B, C, D, A using KVL, we get basically when I'm using KVL. Okay, Kirtana, can you just state what KVL is once, and what is your understanding behind KVL?
The sum of the EMF and the potential in the resistors is equal to zero.
Look, it is all about the loop. It means loop is something from where you started. You are supposed to end at that particular point. Okay, so it means it is starting from some terminal. Okay, understand? It will be starting from some terminal. It can start from here. You can start it from here. You can start it from, but you should be applying it proper. Okay, assume I am saying it now. There is a current I1 flowing in this. Okay, This is the circuit of, okay, because this is a complete normal circuit. There's no other branching is there, so you can say I1 is also there. So instead, I can simply say this to be the I because there's only one current. Okay. So Ketan, assume I'm starting loop from this particular terminal. It means I'll be going in a whole loop and I will come at this particular point. Okay. So what I wanted to say, Ketan, is what is the current potential at this point? Make it as VB. Okay. You are going in this direction, right? So Kirtana, in which direction you are going? Are you going in a increasing potential direction or decreasing potential direction? At this particular point, Kirtana, look, you are here. Okay, you are going now here. So you have reached at this particular point. So you are going in the direction of increasing potential or in the direction of decreasing potential.
Decrease.
Decreasing, right? Because here potential is higher, here is lower. So can I say that it should be minus because look, whatever the potential is there, that is IR across this one, but it is decreasing because you are going from higher to lower, so it will be minus. Okay, you reach here. You don't have to mention this VC now because we are not stopping at this particular point. Okay, we are still moving. We are still in the continuous motion. We have started here because we were sitting here, but we are not resting here. Okay? We are going further. So when you go further, you can say this I got E2. Okay, from here, Kirtana, where you are going? Are you going from lower to higher or higher to lower?
Lower to him.
Lower to higher. So I have to write E2. Can you, Kirtana, complete the rest of the part of this portion? I would just want to come to the B2 again. VB again. Okay. Can you complete the rest of the part? I have reached at this particular point, but I don't want to stop here. I am still moving. Okay. Whenever you stop at this particular, let's say you have stopped here, now you can simply say whatever you have got till now is equals to VD. If you stop at this particular point, but you are not stopping, you are still moving, so you can just move further and tell me if you move from here to here also, what is the next portion you are supposed to do? Your stopping point should be this right now. Okay, you started from your stopping point should be this. Okay, so just complete Kirtana class is about to end, so I don't want to extend it further.
Minus IR2 plus E1.
Okay. Minus how much?
IR2
Minus IR2 and
plus E1.
plus even. Okay, what it should be equals to?
0.
No, it should be equal. Look, you reach here, right? Are you going further? No. So you are stopped there, right? So you can simply call it as B. Okay, understood?
Yes, sir.
Okay. So why you said zero? I know that thing. Because I said sum of all EMF of a loop and potential drop across the resistor is equated as zero, right? So that's why you told us zero. But again, at the end of the day, Kirtana, you will see this VB and this VB is going to get cancelled. Now you can say sum of all the EMFs. Okay, in this particular loop, when you started from here, sum of all the EMFs, sum of all the potential drop. Now you can say minus IR1. Isn't it equals to zero now? This is what I meant. Okay? When I was writing these two, these were just a points. Okay, these were some of the terminals. Understood? So Kirtana, if I instead of moving till this point, like this point, if I would have stopped there, so you can say that I will never get this point. I will simply get AB. And from if you get AB, you can simply say, if I ask you what is V minus AB, like potential difference across VA minus VB, you can calculate, right? So understood, if you want to calculate potential difference across two terminals, you just have to travel, right? You just have to travel from that terminal to another terminal, okay? And you will get the potential difference across this whole. Is that clear, Kirtana?
Yes, sir.
This is a one way. Okay. Yeah. Also, because this I and I is same, so you can say that I times of R1 plus R2 negative is equals to, like, okay, this is an addition, so E1 plus E2 is equals to 0. So I comes out as E1 plus E2 divided by R1 plus R2. Like these are some ways, Kirtana, you can solve the circuits by using two important loops. Okay. Now let's look at the application. Application. When I say application, I am talking about one problem. Application of cable. So I am just giving this circuit over here. Okay. So this is 2 ohm, 3 ohm, 5 voltage, 5 ohm. Okay, and 3 ohm. So you can consider this to be 10 voltage, 4 volt ohm, and this to be the 20. Okay, here's now how you should apply loop here. Look, if I ask you to Kirtana go in the loop, you know you can start by moving. You will say 20 here, but how you will getting the potential across this? You need a current so that you can say that okay, I into the resistor will you give the potential difference. Is that clear? So Kirtana, you don't have to worry about whatever the direction you have to choose, okay? Because at the end of the day, this negative and positive sign will suggest you whatever the direction you took, okay? So for now, just assume that I am taking two directions. Okay, I am saying my loop, my this loop current contains current I1. Okay? Because I am going in this loop. My this loop is having current I2. When I say this I2 mean to say Kirtana, all the components in this particular loop contains current I2. All the components contained in this particular loop contains current I1. So you will see Kirtana that 4 ampere is the someone who is common in these two loops. So you will say, sir, which current I should use, I2 or I1, right? So Kirtana, what happens is we have to use both of these loops individually. Okay. So assume that I am going in the first loop right now for loop 1 KVL equation. You have to make equation. So Kirtana, I am going from here. Okay. I'm going from here. Let's start from here to here. So you can say the potential difference across this one is minus 20. Right now, I'm not going from any terminal to terminal. I'm just started with this one. Okay? Now I reached here. I told you current is in this way. This is the direction. So you can say current is in I1. So you can simply say it is dropping like this. So resistor is 2 times of I1. Then you reach this 4. Kirtana, look at the 4. If you see this 4 resistor, due to this loop, it has a current downside I1, right? Due to this loop, it has current upside I2. Is that clear, Kirtana? So what is the total current across this? You can say either I1 minus I2. You just have to care of the direction. We are going from top to bottom. So let's say that this is greater, this is lesser. So you can assume I1 minus I multiplied by the 4. Okay. You reach here, you are going this way, so minus of 10. Okay. Then after that, you are here, so you can say, can I just make this is fine. Now it's fine. Okay. So minus 10 minus times of I1 3. Do I have any other component? No, I have already covered all. So this is equals to 0. Any doubt here on this first equation? Equation 1.
No, sir.
Okay. I don't think you may be having any doubt. If you just simplify this. Okay. If you simplify it by your own, it will be like 9I1 minus 4 times of I2. Okay. And yeah, it should be minus 30 is equals to, okay, plus 30. This should be plus 30. Okay. How this came out, you can simply say this is 3I1. From here, you will be getting 4 times of I1, and from it is 2. So you can say when you add all of them, you are getting this. This is the Kirtana first equation. Now I can apply loop for 2. If you apply second loop, what you are supposed to get? I will directly give you the answer for this. Okay, Kirtana. So I will just go a bit in a fast manner. So Kirtana, wherever you want to start, you can. You can start from here. You can start from here. So let's say I'm starting at the 3. So across this 3, I'm going with I2. So I will say minus times of I2 3. This is minus 5, I'm going to 5. Here it is minus 5 into resistance. So I 2 times of 5. When you come up to this, you're going upside. So you're adding it. Again, you are going in the direction. So already we have assumed I1, I2 is greater. So you can, in this say, you can say um, I2 minus I1. Okay. And this is negative. So this whole thing comes out as 0. Okay, because I have calculated taken all the circuits. So when you solve this, you are going to get I2 minus 4I1 equals to 5. So Ketna, can you see? If I simply give you this equation circuit, you won't be able to solve it, right? The current, because you don't know direct series and parallel multiplication. But if you see now, you have two equations having two variables. Now you can solve this. Can you solve this? Two equations with two variables. you
Yes, sir.
you can use any method you want, like elimination, substitution, whatever, and from here you will get I1 something, I2 something. You can solve it using these two equations, using equation 1 and equation 2. Okay, so yeah, Kirtana, that's all for the today's class. We have covered KVL, PCL. Okay, if you have any sheet which you are preferring to solve more and more problems, if you don't have, let me know, I will give you the sheet also. Okay, try to solve problem. Um, do you have any doubt in this chapter from the day we have started? Current electricity. I'm not asking about the previous chapters, which I know you have a lot of doubt. Okay. But yeah. All right, Kirtana, if you don't have any doubt, we can end the session by this, I hope. Right? Okay, I'm ending the session.